So yeah, so starting so
when they release the new season.
Oh, you're good.
January to May, June to August is the target.
Oh. Yes, I'm still my coffee. I didn't, not yet.
Hi everyone, Robert is our first speaker. He'll be presenting on sliced elastic distances for global climate model validation.
Right. Yeah. Welcome everyone. Yeah, I'll go ahead. This is my paper I've been working on with Trevor and Bo. It's been a few years and it's gone in many directions, but it's been interesting, been going well. So yeah. Okay. Right. So our goal is to validate something that we'll call the CMIP6 climate models, and we'll unpack what that means a little bit. But basically, we have climate models, and we want to know if they're good or not good. And so our approach, which is the classic approach, is going to be to use a metric, of course, to compare each model to some ground truth. And in this case, the ground truth is called reanalysis data, which I'll explain a bit more in a minute. And so we want to create a metric that uses both the spatial and temporal information, which other methods have struggled with, and also distinguishes between different sources of variability, right? So if you have a climate, the Earth's climate is very complex. It's not just you're more right or less right. You might be more right in certain ways or less right in certain ways, or in certain places even. And so what we've come up with is these distance metrics, or this sort of joint distance metric called the sliced elastic distance. And this is where we take climate models and we utilize this prediction approach to reduce the dimensionality. And then, once these are in one-dimensional functions, we'll use this elastic functional data approach, which is really nice because it sort of respects the temporal order of observations. So first, let's unpack what we mean by, our goal here, validating the climate models. Right, so first we have climate models. Everyone's probably familiar with the idea of these. And climate models are computer simulations, right? The big computers here at NASA or wherever. And they're physics-based, so a bunch of differential equations, these deterministic but really complex systems that characterize climate conditions, and they're tuned to match the true climate on the Earth. So we'll be using the latest sort of ensemble of climate models called CMIP6. This is just a climate model intercomparison project is what CMIP stands for, and it's sort of a standard for all different climate models to be able to compare to each other. And we'll be using monthly data across the globe from 1979 to 2005, and the specific ensemble of models, which isn't really important here. The variables, I'll focus mainly on surface temperature today, but we also apply our method to the precipitation models as well. And so that's really what the climate models are. And as far as our ground truth, right, we want to compare these models to what really happened. Well, our best idea of what really happened is called the reanalysis data. So it's observed data like weather stations, and that's augmented with all kinds of remote sensing data. So you may say, why don't we just use observed data, right? We track weather all the time. Well, we don't really have a weather station placed in some far off corner of Antarctica or specific places, all across different continents. So we need to fill those gaps, obviously, with remote sensing from satellites. So we may have a satellite that is able to measure some radiation across the globe, or I don't know. They measure all kinds of stuff that an atmospheric scientist could probably tell you more about. But the idea here is that since it's based on the observed data, you're able to recreate the historical conditions at a really good spatial and both temporal resolution as well. So we'll use what's called the ERA 5 reanalysis. It's a standard. It's really, really detailed, and it's from Europe. And we'll compare this to the NCEP reanalysis, which is a different sort of idea of what the ground truth might have been. And the idea behind using two different reanalysis data sets is, there's climate models, which are completely computer-based, and they're not based on the observed data. They're not tied to the observed data directly. So two reanalysis data that are both trying to emulate, what really happened are going to be much closer than, one reanalysis and one climate model. And actually, some previous methods have had trouble distinguishing, if you throw in a reanalysis with a bunch of climate models, they have trouble recovering which one is the reanalysis. If you sort of calculated a bunch of distances and removed the labels of which model you were comparing, you want to be able to say, okay, this is the best one. Obviously, this is the other observed data or the other reanalysis data. All right, and of course, our other part, starting from the other end of the more mathematical side, what are these elastic distances? Why do we want to use them? Well, typical, predictive metrics that we use, like R squared and RMSE, they're treating all differences between two models or two functions, I guess, in one dimension, like these two functions, as vertical variability. And by vertical variability, I mean a cross-sectional metric, which means, okay, for observation I, or in this case, since we have time series data for time t, we compare, at time 0, we compare, okay, blue model is 0, red model is 0, they're the same. All right, but at time 0.1, the red model has a higher value than the blue model. And at time 0.5, the red model is now lower than the blue model. Okay, so vertical variability that we always use, it sort of looks like this, where you're comparing the y-axis, the difference between the two functions on the y-axis. And what we're seeing here, if these were two, if this red was, the real climate as we, go to the summer and into the winter, and the blue was a climate model, we see that the climate model is doing a really good job of saying it's going to get, 1 degree hot in the summer and negative 1 degree hot in the winter. It's just doing a really poor job of timing those seasonal transitions, basically. So it's saying we have a late summer, by a lot, and a slightly late winter. But when we compare this with, like a Euclidean norm or RMSE, as we like to call it, we're going to be comparing them vertically only, sort of ignoring the horizontal aspect. So the idea behind the elastic metrics is that they're going to separate amplitude and phase variabilities, right? So instead of just comparing functions up and down, we will first compare them left to right. So this idea of phase distance is the variability due to seasonality, or this horizontal variability, what's the optimal alignment if we were to shift these functions so that they match each other. In this case, they would perfectly align if you were able to warp the time. And then the amplitude will be this post or time-aligned comparison of the actual climate conditions. So if you took this blue model and shifted it, time-wise to the red model, there's some perfect time alignment that could occur such that you actually have the same underlying climate conditions going on. And of course, this can look different ways as well, right? In this figure here, we see both horizontal and vertical variability. So how would we more rigorously define this elastic distance? Well, we have two functions. F1 we'll call the red function, and F2 we'll call the blue function. We convert them to square root velocity functions, which are basically just sine square roots of the gradient. The difference with these SRVFs, as we call them, is that they sort of encode the shape rather than just the exact properties of the original function, and they're a little they're not going to take into account sort of the bias, the change in the intercept between the two models. So we represent these two functions as their gradients. And then we align those gradients. And the reason we're doing this time alignment on the gradients is just because, well, it's mathematically actually a real sort of distance metric that we're getting. So the properties of which I'm not going to go into it all today get kind of messed up if you just work with the original functions. So this warping function is defined as sort of this minimizer over all time warping functions, such that the gradient for function 1 is aligned to the gradient for function 2 once you've composed it with that time warping. So in this case, okay, that sounds really confusing, and of course I'm not spending a lot of time on the functional data part here. What that really means is we take this blue function and we would sort of shift it over to the left so that the peak of the blue function matches the peak of the red function, and the value of the blue function matches the value of the red function. Well, I guess in this case, we really visualize this easier with the red function, right? So if we take the peak of the red function and move it onto the peak of the blue function, and the value of the red function, move it onto the value of the blue function, we get this sort of gray function in the middle that you see. So the gray function has the exact same sort of scale as the original red function, but it's aligned in time to the blue function. So that this horizontal variability, we define how to make that shift using this warping function lowercase gamma. The amplitude distance would be the typical like Euclidean norm between the aligned red function, this gray function, and the blue function. So that's very normal. You know, we align two functions and then we just calculate, you know, what's the usual difference between the two of them. And then the phase distance is sort of defined as the severity of this warping. So amplitude variability is this up and down variability, and the phase variability is this left and right variability. So we do the phase alignment step first, and that gives us an idea of the phase variability, and that leaves us with an aligned function that we can then use for the amplitude variability. And also there's this translation distance. It won't be too, well, it has some meaning in climate, but in this case, you know, these two functions have the same intercepts, so there's zero translation distance. But so if two functions have the same shape, they're just shifted up on the axis, that wouldn't make a difference in this functional data. Is everyone comfortable with these ideas of amplitude and phase variability? Yeah.
So like gamma is something that lets you shift from the red to the blue, right? Like it lines the, so what does that look like in like this example? What's the space? Like what's capital gamma?
Yeah. So wait, capital gamma is the space of boundary preserving diffeomorphisms of the unit interval, which sounds really confusing, but that just means it starts at 0, it ends at 1, it's monotone increasing, and there's sort of like a whole space of those functions. And this function here, this sort of is an arc length from 0 to that lowercase gamma in that on the geodesic or whatever.
Okay, but that's like the dimension of that space is the same as the dimension of the functions mapping. What? So if I have like two-dimensional functions.
Oh, I see. Right, that dimension of that space. Yeah, it's just it's always going to be the same. It's always because there's only one time dimension, right? So we don't have two time dimensions, right? So it's going to be the same as the dimension of the time, which is always going to be sort of 1, I guess, here. So even if you had really, you know, there's some people that'll do, yeah, functions of 3 variables or something with one function or with one time, and it's still, yeah, one-dimensional warping function. It looks a lot like an optimal transport map, actually, if you've seen that before. But of course, these are time series. So yeah. So yeah, but I mean, basically here, you know, if we had an example, time 0 would go to time 0. If we see, okay, red function at time, you know, 0.1 is going to the blue function at time 0.3 or something, right? So it's just a set of instructions on how to move the red function so that it aligns nicely under the blue function. Or I guess actually it's even more than I was saying there. It's more like 0.5, right? But okay. Right, so what's the, we have these elastic distances. Now we want to adapt them for high dimensional functions, or in our case, climate models, which is, you know, okay, we're being a little less rigorous, you know, calling a climate model a high dimensional function. But, you know, one big thing actually that Austin just mentioned is, of course, there's only one sort of time alignment going on. A climate model has a lot of different, you know, locations and areas. So we want to allow for different time warpings across different dimensions. So let's say a model does really well at predicting the weather here in Illinois, but it doesn't do as well at predicting the weather, you know, down in the Antarctica or something, right? You're not going to want to force the same time warping to be applied in all areas. You may allow for some spatial variability in the seasonal variability, right? There may be some interaction between types of variability. So our sort of idea here, and we'll start with sort of this idea of these p-dimensional functions. So we have f and g, instead of being these nice one-dimensional curves, they're now these, you know, whatever dimension we want, whatever finite dimension we want in this case, from 0, 1, which is that time. So f of t, f of 0 to 1, would map to a p-valued real, I guess, right? So you can imagine p stands for pixels, I guess, in this case, or it's obviously commonly used for dimension as well. So if there's a bunch of pixels that this climate model is evaluated at, there's 10,000 of those, and this would be R 10,000. And then we want to apply a projection, or a number of projections actually, but you know, we pick some space of projections that's also p-dimensional, the same dimension as our output, and we want to you know, apply those to f and g. right? We're gonna have to choose that space of projections. But why are we doing projections in the first place? Well, if f is p-dimensional and we have a p-dimensional projection, then if we take sort of the dot product there, we'll have a one-dimensional function. So we have high-dimensional climate models, and we'll apply a sort of projection at the same dimension such that the dot product is now in one dimension. So once we take these climate models and convert them to one-dimensional functions, we can then apply our same amplitude and phase distance from before. So the sliced amplitude will be defined as the integral over that space of projection functions of that amplitude distance, so the post-aligned L2 norm, I guess, in this case. And the phase distance will be the same. We find the warping function gamma by aligning the projections of those SRVFs, and then we'll integrate over that space as well, sort of find the average phase distance in that space once the projections are applied. Okay, so yeah, this is a bit mathematical, but it actually will have a really nice interpretation. But the one thing I've sort of left up to understand here is how to choose this projection space. And a related question would be, okay, these climate models are actually these big spatial fields, so how can we really treat them as these functions that have no structure, right? So for appropriate choice of theta, we want to, yeah.
Making sure that I'm following, would you mind going to
Yeah.
5? That is the one before.
Sure.
So my understanding is that, okay, so you have two, let's say two models, F1, F2.
Mhm.
Climate model, we don't care where does it come from. It comes from some climate knowledge that we have.
Mhm.
So then you're defining another function of I'm assuming the only assumption on F1, F2 that you're saying is they're only to be measurable and they're defined on a Euclidean stance. I mean, not
Yeah, they need to be absolutely continuous, but that's actually in practice, that's not ever a real issue because it's discrete anyway, so you can fit a continuous function through the points.
And just you would like to sort of finding and using some sort of distances based on these two measurable functions to be able to just projecting them, right? And up to now, I do not see any statistics. That's what I want to mention. Right?
Yeah, right. Yeah, no statistics, right? There's actually not a ton of statistics,
So,
which is funny, but.
Having said that, with you in the next slides, I'm not just kind of understanding your projection. So what's the projection function?
Right. So on this slide, right, we need to work with one-dimensional functions in order to align them and get the amplitude and phase distance. But we know for climate models, these are actually, not just a one-dimensional function. They're very complicated, these sort of spatially and sphere-related high-dimensional functions. So all this is saying is in order to apply, the previous one-dimensional amplitude and phase, we need to choose a matrix, a projection matrix, which will let us do a dot product, and that dot product will turn our, 10,000, pixel climate model into sort of just a time series. So we take this projection helps us to turn a spatial field into just one scalar. And then this is why we do a number of projections where we integrate over this space of projections to find this distance. So yeah.
Okay, that's it. So you're saying that for some projection, which we have not like given any close form, it would like to have this kind of distance defined on it, right?
Yeah.
And so intuitively, that projection is what you're aiming for to estimate, right? You're parameterizing it with theta, and you want to estimate it.
Well, yeah. In this case, actually, we can just choose theta, and it doesn't really. You don't really need too many guarantee or too many conditions on theta to have a good distance. But I think the next slide will help clear this up for you. So, but I think I'll check back after that. So okay. So how would we choose a choice of projections? All right, and keeping in mind we need to incorporate this idea that these climate models are spatially and temporally, well, we have the time already, but we need to incorporate the space. So some choices that people already use, it's not really projection, but it would fall under our idea of projections, are the global mean. So if we take every single location in a climate model and just take the mean of all those locations to get, one time series, that is sort of related to the same idea of projections that we're using. So if you took a global mean and applied it to each climate model, then you would just be saying, okay, find the elastic distance between the time series that results when taking the global mean of the over space at all times, right? So that's sort of a projection. You have a 10,000 dimensional climate model, but you're turning it into a one-dimensional time series by just taking the mean. So that's a common approach people use all the time in a climate analysis. Another common approach would be just to take a single location. So the projection matrix would be 0 everywhere and equal to 1 at a single location. And so that's sort of a different idea of a projection where we're only looking at one location. And there's this idea of random projections. So this is used commonly, especially for the sliced Wasserstein distance, which this is inspired by. They use random projections. So, if we have this giant space or if we need to choose a space of projections, why not choose, the most general one? You could get all kinds of different views of the data this way. And so, yeah, these three approaches here at the, everything but this radial projection approach, well, this is commonly used as well. But these are sort of approaches that previous methods have used. They're not really defining this set of projections, but implicitly they're summing over all the locations in the data set, taking a global mean or doing some random projections. People have done similar things before, not with the elastic distance, but with other metrics in order to sort of reduce the dimension of the data or some other nice qualities. So yeah, some problems with these other methods would be, okay, if you take a global mean, that means I'm taking a function in North America and I'm averaging it with a function in South America. But they have different seasons, right? Obviously, there's opposite seasons on different hemispheres of the globe. So for functional data, this global mean is actually not ideal, because if you take two functions that are out of phase with each other and average them, well, this is sort of the issue that we're trying to avoid with elastic anyways, right? If two functions are out of phase and you average them, then they'll just cancel out. You're not really going to get any useful information that way. And that you see the same issue with the random projections as well, right? If there's first of all, it's not very interpretable for climate to do a random projection. But second of all, if there's locations with a high weight in one area and a high weight in another area, and those areas are out of phase, then the projection is just not going to make much sense. And so what people will do also is they'll take each individual location. So this integral would actually be an instruction to say, take every location on the Earth or that on this grid of the Earth, and compare the distance between the two time series at those locations. But as we're using the elastic distance to allow for temporal errors, if you just compare singular locations, you're not really going to have any tolerance for spatial errors. And as well, the models come out at all different resolutions. That some climate models may have a spatial resolution that's only 5,000 locations. Some climate models are going to have millions of locations. So comparing individual locations doesn't really make sense when you don't have a common set of locations. So our solution here is these radial projections, right? So it's sort of like taking a singular location but using information around there. Of course, this looks a lot like a method using in image processing, right? Like a Gaussian blur filter or kriging in spatial statistics. And the idea here is that nearby locations like Champaign and Urbana are going to have similar phase. So you don't run into the same issue with these out of phase functions in a global mean. Yeah, so I guess tying it all together, right? Our idea here is going to be to, okay, so this integral is really telling us to slide this radial projection over the surface of the Earth and calculate the resulting one-dimensional functions. So at different locations, how does the climate model, compare to the reanalysis? And I guess I'll show a little bit of what that looks like in a practical way too. Right, so if we have the reanalysis field and we have a climate model and a radial projection. In this case, this radial projection is centered actually right around Champaign, Illinois. Okay, if we take this radial projection, which is 0 in all these dark blue areas and 1 in this yellow, radiating outwards from 1 in this yellow area, if we take the cross product of these two areas, then the result is just going to be giving us weather information about Champaign and surrounding areas. So we apply the same projection to the ERA 5, the reanalysis, and the MCM, which is a model I've chosen because it has some shortcuts that mean it's not going to be quite as accurate in certain areas. Then we get these dots here. So the area 5 has an average monthly temperature of -15, according to this projection, and the MCM has a temperature of closer to 0. So already there's a bit of a discrepancy. This is a particularly bad month for that model, which is fine. And of course, the model is not really trying to just model the observed data. It's sort of its own independent thing, but that's still trying to recreate the historical conditions. So if we continue on and we take this radio projection and multiply by January, multiply by February, and so on till next January, we'll get a whole, of course, like a nice thing here where we increase in the summer and cool down again in the winter. And we see, okay, the model is very close to the area 5 for most of the year. It's just sort of this winter and this summer that were the issue. And okay, this is a little hard to see, but the model is shifted a little bit to the left of the data. So we would also say there's a little bit of phase variability there. And if we continue on, of course, 10 years and all the way to the full extent of our reanalysis data that we're using, we can say, okay, the weather, according to this radio projection, which is centered around Champaign and including areas around, the weather in the model is a little bit hotter usually than the weather in the reanalysis. And these tiny differences in the phase in the horizontal shift, which aren't very apparent in this particular location, would constitute the phase distance. And of course, this is just one projection. So we've used this sort of kernel filtering sort of a spatial approach to turn these two high-dimensional climate model output into these time series. And we can repeat this for different projections. So if we move the projection around the ocean, now it's really warm all year. And there's definitely bigger shape differences between the two models, or between the model and the reanalysis. Of course, in this case, the model is greatly overestimating sort of the year-to-year variability and getting a lot of the timing wrong too. Maybe this model doesn't account for certain multi-year trends like the world has, in truth. And I guess one thing to note about these radio projections, it may just look like sort of a Gaussian blur filter, but there's a little bit of a difference if we move the center of the projection up to the North Pole or down to the South Pole, it's going to get distorted, right? So first of all, of course, we're on a sphere, so we're kind of connected at both ends, which makes sense. And these grids are sort of evenly spaced in latitude and longitude. They're not evenly spaced on the globe, so there's actually more points in these areas close to the poles, which is why this sort of gets stretched out and distorted. But either way, you can see how the model fits to the reanalysis here. Overall, it doesn't look too bad, although this sort of variability in the peaks here are a little different between the model and the reanalysis. And yeah. So okay, so now we have these three projections we're using. Each of these is a different functional data. And if we sum over these, then we're sort of approximating that, or sort of a Monte Carlo approximation to that integral that we had before, which lets us look at different views of the data. So does anyone have questions about sort of the method so far? This is probably I'll start talking about the analysis soon too. No, yeah, I used to use these random projections. I think I did something. There you go. Right, so I used to use these random projections, and the issues I had, which I won't fully explain today because it's more of like a simulation section thing in the paper eventually. These random projections had issues where, okay, so when we're comparing two functions, right, the reason we use elastic functional data is because these two functions, while they have the same overall shape, they're just sort of out of phase with each other. And of course, we'd use the elastic to get them in phase. Okay, so what we're saying is we shouldn't take differences of two functions or even linear combinations of two functions that are out of phase, right? Well, when we switch to the global mean or the random projections, what we have is areas in the northern hemisphere that have winter in December, and areas in the southern hemisphere, okay, that would have winter in June, right? So now these two functions are out of phase, and when we take a projection, it's essentially a linear combination of those individual functions. So the problem, I guess, to summarize with the random projections is that before we do the elastic, before we even use the elastic distance, we're already committing the thing we don't want to do, which is taking, combinations, doing operations on functions that are out of phase. Right. So yeah, if we do this combination and then do the elastic distance, we're kind of being rigorous in one way and really ignoring the issue in another way. But yeah, that's sort of.
So that's why in the simulations you got like you always had like an amplitude distance.
Right. So what happens when what's happening when you don't do a proper phase alignment is, of course, the amplitude distance, the true amplitude distance we would say is actually 0. But if you do an improper phase alignment, you're going to inflate the amplitude difference. So if you don't pay attention to whether functions are in phase or not, you're going to think they're really out of shape. They're really different amplitudes. Yeah. Mm-hmm. Yeah, so I guess to be a little more applied here, we're going to apply these to some climate models. So we're going to compare those CMIP6 models, which we can obtain on the internet, to the ERA5 reanalysis. You also can just download that. And now that we have a distance, okay, proper distance between two functions, we can just throw them into that distance and get some comparisons, right? So we're going to generate rankings or similarities between the climate models and the reanalysis via sliced amplitude and sliced phase. We'll include that NCEP reanalysis to see if we can sort of detect the imposter. And we have a few research questions, of course, which CMIP6 models perform the best. That's always interesting. How does the NCEP compare? Of course, and one big thing of interest is, we know about all this, as technology is getting better, we know this idea of diminishing returns. So we want to say, okay, people have been spending all this time and money on climate models. Have they gotten better since the previous era, right? So CMIP6 is pretty new. It's only a couple years old. CMIP5 is more like 5 or 10 years old. So of course, we want to see which one does better. Okay, so we'll start just with CMIP6 and comparing those to the ERA5. So here we have amplitude, sliced amplitude distance on the y-axis, sliced phase distance on the x-axis, and you can see the bottom of the plot is y equals to 2 and x equals to 0.13. So if we were to compare the ERA5 reanalysis to itself, of course we've said that these are sort of proper metrics, so it would be all the way sort of down here at 0, 0, right? So the ERA5 is obviously a distance has this property of identity, right? If you compared the same thing with the distance is going to be 0, right? So if the ERA5 is down here, then of course the NCEP is the closest thing to it. So the two reanalysis datas are more similar. So you'd say the NCEP is closer to 0, 0, which means that it's sort of the superior model in both amplitude and phase here. Which is good. It's not a model at all. They're both recreations of the true climate. So we hope they're very similar. And then the majority of the models lie in the space here, 0.15 to 0.17 phase distance and 3 to 4 amplitude distance. And then there's this one outlying model here that of course we'll ignore as well because it's going to mess with our ability to study what's going on with the majority of them. Okay, so if we just focus on this area of the plot, we get this next plot. Which I think right, we don't know what all these models are, all the details about all of them today. So we're just going to look at, mainly the points just to study sort of what's going on with amplitude and phase. I would say there's like a slight positive correlation between sliced amplitude and sliced phase, right? A model that does well in one aspect might do well in another. If the underlying dynamics of the climate model are really good, then it's probably good, both for seasonal and for those climatologies. Some things to note are if we read these labels or look at these colors, we see that climate model groups, like here's like this EC Earth climate model or group, all those are sort of clustered closely together with each other, which is good. So we're saying, they may have different modifications they do on the models or slightly different models, but the overall ability for one underlying climate model is pretty much the same. These GIST models are NASA models. They all perform similarly as well. So yeah, that's a good thing to see basically when we're doing a similarity metric, is that things that have similar properties are grouped closely together. Right, and I guess to note this sort of are suggesting so far that are sort of, best model, of course, by this particular metric is this FIO ESM2 model. It has the lowest amplitude and the lowest phase. Actually, it turns out it has it definitely has the lowest in both. Of course, some models are like, this CMCC model is really good for phase distance, not as good for amplitude. But might be other models that are really good for amplitude distance and not as good for phase distance. So that there's a trade-off, of course. It's not just a straight up ranking, which is fine. Right, so as far as our conclusions, we're generally able to show, models that are most similar to the reanalysis. And the reason I claim that is because, if we have a second reanalysis that's based on the same truth, it's going to be closer to the first reanalysis than all the models are. And I guess this seems like a very obvious result, right? But actually, there's some other methods that we will compare to in the paper, and they aren't able to show this NSEP reanalysis as sort of an outlier. It's sort of just mixed in with the other data points, or even one of the worst. So it's good that it's really good that our method's able to show that it's different. Obviously, that seems like the basic requirement, right? Right. So we have this weak positive correlation for temperature between sliced amplitude and sliced phase. And as Mo sort of hinted at before, before I had been doing something that resulted in, poor phase alignment. So that really inflated the amplitude distance. So one good thing to note is if you have like a almost one-to-one correspondence between amplitude and phase distance, well, that probably means you're not doing your phase alignment properly, which is causing those improper comparisons where the functions are out of phase. And it's inflating the amplitude distance. So it's good to see a little bit of correlation, but we don't want to see almost near perfect correlation like 0.9 or something. Right, so our best model so far is this FIO ESM2 model. And our sort of outlier model is this MCM UA1 model. So we can use these models along with the NSEP to study the sort of the spatial variation in sliced amplitude and phase. So, right, these projections correspond to, centers with this radial basis. So we can just take the centers and we can make our own map of our own distances. So here's what that looks like. Okay, so here's the sliced amplitude values for the NSEP, for the FIO model, and for the MCM model. Of course, the MCM had the highest amplitude distance. So, spatially, of course, it's going to have a higher distribution of amplitude distance. FIO was one of the best models, and NSEP was the best because it's not a model at all. And I don't know, we can use this to study, where these models are doing really well compared to the Era 5 across the globe. As our baseline, the NSEP seems to struggle probably more maybe around Antarctic, definitely in the oceans here. There's some higher areas and around sort of areas that have constant climate or difficult to model climate. And when we compare, a model to the Era 5, okay, now it has sort of the same patterns in certain areas like around here that are high, but it has its own areas that it's not doing great either. So I guess up here in Greenland, this model's doing poorly, and maybe in South America that's doing poorly compared to the reanalysis. So this would tell us, areas maybe to look out for, or to sort of develop the climate model around. And then this MCM model has something very interesting going on here. I guess this is, that would be, I guess, depending on how you look at it, you normally would say that's like, yeah, east. What's that? Yeah, right. Yeah, Northeast Asia, I guess. Although even though it's on the west side of this map, I guess, yeah. Yeah, so that's interesting, and it seems to do poorly sort of in some areas of the ocean where other models don't struggle at all. So that's interesting, and maybe you see some coastal effects too. Just along the coast of these countries, it's higher than in the oceans, which is interesting. And you can do the same for phase. That's not as interesting because relative to space, areas in the middle of the ocean, right, and the equator are not going to have very much shape at all because the climate's not really determined by seasonality, but just it's more constant. That's going to make phase alignment a little bit harder, or at least introduce more opportunities for phase alignment. So if you had a particular area of interest, it would probably be better to zoom in on that area. And I'll cut it off here. Right, so I've already done this for sort of a previous version of this metric, but I've changed things. So I need to repeat the analysis for CMIP5. And then you can sort of say, okay, here's the CMIP6 scatter plot. And maybe the CMIP5 scatter plot would be more over here. And you could say, CMIP6 is closer to 0, 0, which is a good thing. And then we'd want to say, okay, do the results change when we compare everything to the NCEP instead of to the arrow 5? Spoiler alert, doesn't really change, which is good. And we want to repeat this for precipitation to do some of those comparisons again. And then one thing I haven't shown here that would probably be interesting and answer a lot of questions, but there's not time for is, right, we want to compare this metric to previous methods. Of course, I've made claims that this metric has this nice quality where the NCEP is separated. So it'd be good to show some other methods that don't have that. I've also done a lot of simulations on these radial projections versus random projections or versus the global mean. And it really shows less correlation between amplitude and phase distance, which is a good thing, especially when you design a simulation such that they shouldn't be correlated at all. And then this radial projections are like a kernel, right? And there's a underlying kilometer-based range parameter for those kernels. So I have some simulations to motivate those as well, and to show sort of the best choice. But yeah, for now, are there any questions? I guess I don't have too much time before it's Eddie's turn. So let me know.
What kernel are you using?
Yeah, so right now it's a Wendelin kernel where the range parameter it's made to sort of approximate a Gaussian. So okay, for today, right, it's just a Gaussian kernel where the range parameter corresponds to the area at which the correlation is 0.05 or whatever. So yeah, I mean, similar to Gaussian blur and image filtering, similar to Kriging and spatial statistics, but based on actual Earth distance and not, pixel distance. Yeah. Thanks.
Thank you, Rob. Our second speaker is Eddie. Eddie will talk about compression analytics for classification using Bayesian context trees.
Thank you. So this. All right. Hi, you guys. My name's Eduardo Cardenas-Torres, and today I'm going to be talking about compression analytics for classification using Bayesian context trees. I'm doing this under the supervision of Dave Zhao at the University of Illinois Urbana-Champaign and Alexander Foss at Sandia National Laboratories. So let's go ahead and talk about what compression analytics even is, right? So what is compression analytics, right? Data compression, the process of encoding information using fewer bits than the original representation, right? It's a really simple sentence to say, but what's the intuition behind it? Is to reduce the number of unique symbols in your data, right? To have the smallest possible alphabet, okay? Encode more frequent symbols with fewer bits. Fewest bits for most common letters. Typically, that's what you're trying to aim for, have a small alphabet, have less bits, so you can compress more data, have more information together, right? So what are the challenges behind data compression? The challenges are the best choice of compression algorithm is depending on your data type. We have different data types, as we all know, as statisticians, right? We have time series, we have spatial, we have different types of data as such, right? Transforming data before compressing it depends on your method, and then many different types of compression algorithms to choose from. So there's going to be a bunch of different ones that we could choose from, and the main type of compression I want us to really focus on is lossless compression. There's another one called lossy, but we're not really going to be touching base with any kind of lossy compression. Today's going to all deal with lossless compression, where we're trying to lose the least amount of information as possible, right? It's a type of class of data compression that allows data to be reconstructed from compressed data without loss of information. So that's really what we're going to be focusing today is lossless compression. So how can we use this for machine learning, right? We're going to be using compression algorithms involve modeling the data and then encoding it. Modeling often includes an algorithm for predicting symbol probability. So we'll see as we go along that there's a specific or different types of compression algorithms use various types of ways to predict these symbols. The encoding stage uses these probabilities to substitute high probability symbols with smaller codes, as mentioned before. Compression analytics uses predicted symbol probabilities for machine learning. And we're going to look at discriminant analysis for classification of data by using those trained probabilities from compression algorithms. So with that being said, our focus today is to be able to use compression algorithms to make a classifier. So that's our big thing today. We're going to utilize some of these compression algorithms to help us classify. And so to give us a little background, just a bit about discriminant analysis, the idea is to model the distribution of X of each class separately as follow, then use Bayes' theorem to flip things around and obtain the following. I think we're all pretty comfortable with this idea by now. Yeah. And then how does compression come into play with all of this, right? Typical compression algorithms follow the following algorithm, right? You have the probability of some symbol given some string, where the sigma represents the predicting symbol right here, and then the S represents the string given. So you're given some string, and then the following predicted symbol is just some character that you're trying to predict, right? From here, we could see sort of an overlap between compression algorithms and discriminant analysis right here. So you could sort of see, right, you're given some kind of string, you're trying to predict some probability based off of this, right? So how can we combine this? Which kind of compression am I going to be really looking at? And that's the next part, is called prediction by partial matching. So this is the main compression algorithm that we wanted to look into at first to see how we could incorporate it with some type of classification. It is a type of lossless compression, and there's different various types of PPM to handle an unobserved character in a string. So PPM itself has various different types of algorithms to itself. So the basic idea is it uses the last few characters, in this case, the context, in the input stream to predict the upcoming one, right? How does the algorithm specifically work? So right here, so you can tell, if you've seen this character, you're going to predict, or if you've seen this string in the past, you're going to help predict the following character. If not, you're going to see this thing called escape. Okay, and we're going to talk escape a little bit more in a second. Right now, it may seem a little weird, but right now, I'll explain it as we go along. S represents a sequence prior to sigma, the predicted symbol. This SAB, I know we're not used to this. I'm not used to that either when I first saw it, but that's how everyone in the compression world represents this. It denotes the sequence from index A to B, right? So that's a big thing for us to note. This right here, SA to B, is the same thing as n minus d plus 1 to n. Cool, so that's just the string that you've seen in the past. And n indexes the position, and d represents the order of a model. Yes.
This SAB is literally like a substring operation in code, right? Like
yes.
Letter 1 to letter 2.
Yeah. So like if you say the word car, the substring from C to A would be like 1 to 2. Does that make sense? Is that clear?
Both sides inclusive.
Yes, both sides inclusive. SA without B? So like an example?
In the top of your piecewise function, yeah, there's no upper index.
That's just implicitly to n, right?
Yeah. Yeah, that's implicit. Cool. Any other questions?
So that would be, what would that be, the remaining string? So from point n minus d plus 1 to the end of the string?
Yes. Yeah. Beginning to the end. More clear?
So what is the subscript D?
Yeah. So this D right here, right? This represents the order of our model. So the order, I was going to get to that in a second, represents how long of a substring you're looking at, right? So if I'm looking at a word that has 3 strings, it's specifically an order model of 3. So that's what order represents. If you want to look at a word that's 5 characters length, or anything 5 characters length, that's an order model of 5. So it's dependent on the length of the string that you're already looking at. And you could set the order to be smaller too. It doesn't have to be the length of that word. It could be 2 if you're looking at a character word of 5. Does that make sense? Yeah.
And so So what is the probability model P hat D?
This one?
Yes. So you changed from P hat to P hat D, right?
Yes. So this one right here is representing, so this whole thing is capturing every single possible model or model order that you're given in PPM, because PPM captures all different types of orders together, right? PPM specifically has a bunch of different Markov models.
So P hat D's are given.
Yes. Yes. Cool. Yeah. All right. So how can we use PPM for classification? It's actually, it looks pretty nice actually when you go through it, right? We have the general discriminant analysis up here, the PPM algorithm that I showed before, just right here, right? And then when you combine it all together, you just get this here, right? You just got to include some classes into the essentially the PPM algorithm, right? You get some sort of classifier out of it. But there's some disadvantages to it. PPM, right, has an escape method. So the method, the algorithm that we showed before right here, this escape method is not proper in a statistical manner, if that makes sense. And I'll explain in a second why. So it uses an ad hoc approach to its smoothing mechanism for its missing values called escape. So if you're trying to predict a symbol that's never been seen before, what it will do, what PPM does, it just goes to the counts of each different symbol and tries to put it in there. There's no specific statistical reasoning why it goes to the next character. All it does, it moves down to Markov model and picks the highest count order of a letter. So that's a disadvantage to us in when we're using this as a classifier. Yes.
So to make sure I'm following, when it escapes, it says it can't find. I've never seen this letter before, so
Yeah.
I'm going to choose the modal
Yes.
character. So if A appears the most common,
Yeah.
then whenever I escape, I'm going to say that should be an A.
Yes. Oh, actually, it doesn't. Actually, it goes up to just whichever one is greater than 0.
So the next least. So the
Yeah.
it's the minimal
Correct.
appearing letter. So if I have C, it has appeared once.
Then you're putting it
If I have
in
a
there.
character that I haven't seen yet, I put
Yeah.
it as
Yeah, exactly. Does that make sense? Right. There's not really any good statistical modeling to this or exactly a proper probability model like we're used to, right? So the escape mechanism moves down to one order model lower and check to see if the count's greater than 0, then utilizing the orders count for prediction, right? Potentially leading to a decrease in overall accuracy and affecting the PPM classifier rather than just getting a count greater than 0, right? So how can we overcome this using a compression-based algorithm that helps classify, right? So we can't go to PPM. What's the next step we could go to? We can go to building an optimal naive-based classifier using what's called a Bayesian context trees. That's one thing that we could really focus on. So overcoming a compression-based algorithm with an improper probability model, we could solve this with the help of BCTs, right? Bayesian context trees help find the best tree model within various tree models by utilizing a Bayesian approach. And BCTs can also help compress the data it is working on by incorporating different variable length contexts, right? So when I say that, it's a little insight for the next slide, but it incorporates different various context lengths by giving each different length a tree. From there, they car, I think is an example, right? If you use a lossy compression, it's actually going to take out some characters, like R itself. And so you get CA as a possible way to represent it, right? Lossless will try to keep information that can represent that R, but with fewer bits. That's like the biggest thing with lossless compression. You're using fewer bits to represent that. Does that make sense? And then here, that's what they're doing, right? They have different tree models. More lengths of nodes and leaves is going to provide more bits, but the least amount of leaves and nodes are going to provide less bits, but it could also represent that information. So that's why you could use BCTs as well in a compression realm. Does that make sense?
If I have a 10,000 character string,
Yes,
a lossless method will retain 10,000 characters,
as best as it can.
but the representation of that may be,
Smaller.
2 million bits to 200 bits.
Correct.
Okay.
So that's like the main thing to this. Can we use that to classify now these different data types, right? Jaideep, I can't.
Click in the middle.
Just click.
Click in the middle, yeah.
Okay, cool. Cool. So now let's make this classifier, right? We're typically, I think we all know what a naive Bayes classify form looks like. So with Bayesian context trees, right, I talked about the children, the nodes, the leaves, right? So the Bayesian context trees were given a tree. Its leaf nodes distribution, or the tree is called T, excuse me. Its leaf nodes distribution, theta K, or is equivalent to theta KS. Sorry, I forgot the symbol name. And then S is a part of that tree where K indexes the class. So the following classifier would look as such, right? There's a lot more to it, but I don't think we all want to see that much math in this representation. And with this, we can make BCT classifier to make classifying data a little more precise than the previous lossless compression that we've seen. Cool. So that being said, I don't have any results yet, but my conclusion is that using compression algorithms for classification is a possible connection, right? PPM can be used for classification, but does not have a proper probability model. And BCTs can help us bridge the connection between compression and classification with a proper probability model based off of their tree structures. Okay, and that's all I have. Thank you, guys. Do I have any questions?
Could you give an example case, whether it be with, your method or any method, as to where it would be relevant to use compression as a classification metric?
Yes, you could use like documents, I think, or Twitter messages is one. I think you could even use I was talking to someone about this.
So is that like a sentiment analysis type thing where, like, or is it like this document is a paralegal document, this one is a tweet,
Yeah,
this one is a text message, this,
Yeah.
like,
you could do stuff like that as well.
so it comes down to determining the type of, of like use case for
Correct.
each sequence. Okay.
Where order matters too. Order matters in this case. Cool. You could also use it for DNA sequencing. This was a big deal for DNA stuff. I think they tested BCTs in COVID data specifically as well. Cool. Sorry for the short presentation, but thank you guys. Cool.